right? All right. What's that? No, it wasn't. Like that I had that mixtape, sound bite a little bit ago, and it wasn't on the recording, alas. Okay, let's get started. A couple things. So this is what I'm going to do for homework 6. I got busy this morning. I didn't get a chance to print it out. So I'm going to post it on Blackboard sometime today. And instead of making it due, if you go to the syllabus says it'll be due on Wednesday. What I'm going to do is make it due on Friday. Now, I'm still planning on canceling class on Friday, next Friday. So I'm just going to have a box outside my office. You all drop it in and keep it simple. Is that all right? Yes. I was going to put it out on Wednesday. And honestly, if you all have it done on Wednesday and you'd like to give it to me on Wednesday, give the homework to me, I'd be more than happy to take it and then have a great break. So I'm fine with that. So I usually don't like to take the homeworks early because I'm afraid I'll lose it. But that day I'll be ready to accept the homeworks if you want to just turn it in on Wednesday. Sound reasonable? All right. A couple other things. So we don't have our second exam in here until after break, but it's going to be on shears and deflections. We're starting shear design today, so today's probably a pretty important lecture in regards to the exams. Everybody wants to pay attention to that. We are still going to cancel class on the 17th. I do have one other announcement. I don't have it on the slide because I really don't know much about it other than the email that I got. Next Wednesday on the 15th, there's a big shindig going on in the engineering building. It's going to be in the structures lab from 12 to 1. There's going to be food. They want a lot of students there, so there's food. There's free food. Does it matter? There's free food. There's free food. Next Wednesday at noon. And honestly, I think I'll know more as the days go on, but I literally got an email that just said, so we want 200 students there on Wednesday. I don't know any more than that. You think I'm kidding. That's all I know. What's that? We'll see what happens, but I don't know. Okay, any other questions? Okay, with that, let me go ahead and get into some concrete design. So let me start off here. So if you recall last time, what we had done is we had taken a beam that had various regions of stirrup spacings, and then based on that layout, we determined what was not only the shear capacity along different regions. So we noticed that different regions, they got weaker as as we went down the beam because they had less stirrups. But in the end, I don't want to say that didn't matter, but that was sort of by design, because if we look at the shear demand, the loads on the beam, it actually made sense that we spaced those stirrups out as we got away from the support, because the shear goes down away from the support. So as long as our shear capacity is higher than our shear demand, we're happy. Kind of like economics, right? Supply and demand. You didn't learn anything? Did I get a sign and she started? See, I grabbed, I'm remembering stuff. It's like a personal victory every time I remember that I need to take attendance. Okay, let me sort of turn to the example at hand. There we go. Okay, so let's talk about how to design. Let's talk about how to actually lay out shear stirrups for a given beam. So let's talk about this a little more holistically. I mean, I think by now, if I give you a beam and I just say the beam's 30 foot long and it's got a factored load of 4 kips per foot on it, you all can size that beam. You can tell me the width, the depth, how much tensile steel needs to go in it, etc. That's something I think you all can do. Now what we've got to do is take that design and reinforce it for shear. Okay, so that's what I want to talk about. Okay, now remember that our primary goal in any design scenario is that our factored resistance has to be greater than or equal to our factored load. Sound good? Well, our factored resistance is essentially our factored resistance. If we're talking about shear, it's the factored resistance that's provided by our concrete plus the factored resistance that's provided by our stirrups. Well, if we're in design mode, one of the things we need to figure out is how far apart do we space our stirrups. So if we assume we're using number 3 stirrups, we can calculate AV and FY and all that. The only thing we don't know in this expression is S. We don't know the spacing. So we can solve for that pretty easily. That's not so bad. Okay? So that's simple. Is everybody okay with this? This is literally just algebra and solving for S. Everybody good? Now, here's where things get a little more detail-oriented, and I want everybody to sort of be clear on what's going on. ACI allows us a couple provisions that make our lives a little easier, and I don't want to say a little, maybe a little more confusing, but you just sort of have to understand what's going on. Okay, number one, let's look at this expression. Okay, would it make sense that if phi VC, if just phi VC is greater than or equal to VU, we wouldn't need stirrups technically, right? Would that be a fair point? Okay, now that's a fair point just from a conceptual standpoint. However, you all have seen footage of what it looks like during a shear failure, and it's not pretty. It's quick. It goes quick, right? So what ACI states, just to be safe and on the side of caution, is ACI states that you must provide stirrups anywhere that our shear is larger than half of phi VC. So there is going to be a region of the beam where we technically don't need stirrups from a capacity standpoint, but we got to put stirrups there to ensure that we are just meeting the requirements of the spec. So we don't need them for capacity, but we're putting them there anyways just because if something were to go bad, it would go bad quick. Okay, so that's provision number one. All right, provision number two, we have to provide stirrups everywhere along the beam. However, if we start getting into contact stresses and bearing stresses right there along the, right there at that support, it can take some time for those stresses to actually propagate throughout the beam. So the way that ACI allows us to, in a way, kind of take advantage of that is they say that we're allowed to actually use the shear value right here to begin our design. I know that the shear diagram continues up and it's technically a little larger right here, but because we have bearing stresses and it sort of has to propagate throughout the beam, it's kind of like shear lag, if you will, in a tension member. You know how we put the holes in the tension member and it took time for those stresses to propagate throughout the beam? Well, if you've got a support right here and you're applying a shear force, those stresses sort of have to propagate before the beam is experiencing that pure shear. So what ACI states is it says D away from the support, that's the shear that you can use for design. I'm not saying you don't have to put stirrups here, you definitely do, but this is the value that you can start to use for design. And that'll make sense as we start to go into a given example. There are a couple instances where we are not allowed to do that. We call this an end shear reduction. There are a couple instances where we can't. One instance is if you've got load applied directly to the bottom of the beam. You're not allowed to do that shear reduction because that crack has the potential to propagate a little faster. You're also not allowed to do an end shear reduction on a corbel. If you remember, we talked about the 3rd Avenue parking garage, and you've got those little sort of stubs that stick out of the columns that the beams sit on. There's a fair amount of shear in that, and you're not allowed to do an end reduction there. You have to design for the full shear, because, I mean, all that shear is going right there, so you're not allowed to do any reduction for that. Now, so like I said, there's going to be some regions in the beam where we technically don't need stirrups, but we're going to put them there anyways just to ensure we've achieved an adequate level of safety. So in those regions, what I'm going to do is I'm going to put stirrups there, but I'm going to space them out as far as humanly possible. So I'm going to use the maximum spacing. Now, our maximum spacing, if you actually go back to some specs we looked at earlier, is actually a function of what our strength provided by the steel is. And what I'm going to do is use the conservative approach and use the top limit. So one of our maximum spacing limits is going to be based off of the capacity of the steel in shear. So that's where one maximum spacing value is going to come from. Another one is going to come from this. We didn't really assess this when we did our last example, but there is a limit that states that no matter what, you have to provide a certain amount of steel, a minimum amount of steel to develop that capacity. If you recall, we had a similar limit for beams. Remember, we had a minimum steel requirement that we checked, and it seemed to never really matter, right? Well, for us, we're going to kind of use that as an upper bound limit for our spacing in those regions that we really don't need the concrete. All right. Sound good? What I'm assuming is that we're not going to get that much capacity out of the steel. That's where I'm meaning when I'm saying the conservative approach. So, and also let's be clear, we're talking about regions where we really don't need the stirrups. You know what I mean? So I want to make sure I'm putting them there, but I'm going to do my best to space them out as far as possible. So, make sense? And I think as we start to get into this, I think you'll see that everything we're about to do kind of washes out in the end. So, and don't worry, we'll get into some examples where we do this, but we're basically going to compute two maximum spacings, or we're going to take the smaller one. So let me get into the procedure, and I think once we start getting into some examples, I think this will kind of make sense. So the first thing that we're going to have to do is we're going to have to construct the shear diagram for the beam. Now this shear diagram is going to be fairly detailed. It's not going to be as simple as just, or like that. It's not going to be that simple. There's going to be a lot going on. And we're going to have three separate sections of importance. We're going to have the section of the shear diagram where we got to have stirrups, the section where we don't really need them, but we've got to put stirrups there just for code demands. And then we're going to have a section near the middle of the beam. If we're talking about just a uniformly distributed load, we're going to have a section where we don't need stirrups at all. Okay, so there's going to be three sections of the beam that we have to delineate, and that's going to take a little bit of work. So I'm going to take my time with that. I will admit I probably should have told you all to bring a straight edge, but when we start drawing the diagram, the shear diagram, my advice would be almost draw it on a separate sheet of paper or draw it really big because it's going to get kind of detailed. Once we get our shear diagram laid out, we need to calculate an S value, a given stirrup spacing to get going. So we're going to start off with the shear D away from the support, that end reduction of shear. We're going to use that S value to begin the design. And then we're going to improve upon that design by using the maximum spacing in the regions that we really don't need the stirrups, but we've got to provide them for code requirements and for just general safety of the design. Now, once we've got our S values, we're going to want to start actually laying out the stirrups for the beam. Step 6, this is where a little bit of experience and a little bit of common sense comes into play, because you might be able to add some additional increments of stirrup spacing and shave off a few stirrups on your design. Let me be clear, during homework problems, I will make it very clear how many regions you need to provide, and the same thing on exam problems, because I don't want you sitting there laying out stirrups left and right. Once you can do it once, you're good. As a final step, because we're using, bless you, because we're using this limit, oh, you didn't sneeze. It sounded like a sneeze. You just ripped a piece of quad paper off, is that what it is? It sounded like a sneeze. That's why I thought it was. Yeah, okay, I'm not alone, thank you. I'm not alone. He thought it was a sneeze, so. Oh, it doesn't. Cordiality does not count as a mistake. I was being polite. I mean, I could have handled it differently. I said, will you all stop sneezing in my class? All right. As a final step, you do want to make sure that none of your shear capacities violate the following capacity. Remember, one of our spacing limits is making this assumption that this isn't violated, so you'll want to go back and check that. I think this is one of those design procedures that it really begins to make a little more sense when you start doing it. So what I'm going to do is get into some calculations and get into constructing this shear diagram and laying out the stirrups for the beam shown. So let's lay this out. So we're going to design number 3 U-shaped stirrups for the following beam. So I got a 20-foot beam. It's 4 KSI normal weight concrete and 60 KSI steel. And to keep things simple, I've given you the self-weight or the factored load on the beam. So we're saying this is 11.5 kips per foot, so it's actually got a fair amount of load on it. And we'll say that includes the beam self-weight, so we don't need to go through and do all of that. I just want to sort of get into the shear design. All right, sound good? All right. One of the things that's going to be important is that we recognize the use of the equations that we derived last time. And if the shear diagram gets a little more complicated, you need to be able to handle that. So let's sort of get into it. Well, you just need to provide yourself a fair amount of room for it, is all I'm saying. And you'll see what I mean when we start drawing it out. I'm going to actually try and use some of the straight line features in this smartboard software to try and make it neat. I would say, that's a good question. I would say that the final answer, to keep it simple, is probably that. The fact that the shear diagram, or the factored shear capacity was always higher than the shear load, so it indicated that the beam was safe. Do that. Okay. All right. Okay. Oh. All right. So, example 13. All right. So I'm going to write down some fundamental beam properties just to get us started. All right. So we've got an FC prime of what? For what? There we go. Now it's normal weight concrete, so I'm going to say that lambda is 1. We don't need the beta 1 actually for this. And Fy or Fyt, doesn't really matter, is 60 KSI. All right. Now we have a B value of what? 16 inches, and a depth of W sub U is 11.5 kips per foot, and L is 20 feet. And we have number 3 U-shaped stirrups. So what is AV going to be? See if y'all remember that. What's the area of a single number 3? 0.11 square inches, so what's AV going to be? 0.22. So we'll say 2 times 0.11. Is everybody okay with that? Now, step 1 is going to be construct the shear diagram. Okay, now let's be clear. This is a simply supported beam. And it's a uniformly distributed load. Okay, now here's how I'm going to handle this. Do you all remember this? VU of X is WL over 2 minus WU X. You all remember that? That was the equation that we derived last time for a simply supported beam subjected to a uniformly distributed load. All right, I'm going to use that pretty heavily throughout this example. Now, WU L over 2, just off to the side, is 11.5 kip per foot times 20 feet divided by 2. So 20 over 2 is 10, so that's 115 kips. All right, does that make sense? So could I rewrite this as VU of X is 115 kips minus 11.5 kips per foot times X? Would that be a fair way of doing that? Now, based on the way that I've written this equation, what can you tell me about X? First off, what is X? The distance from, like, the support. What else can you tell me about X if I plug into that equation? It's got to be in feet, okay? We got a lot of beam dimensions and stirrup spacings and all that stuff that's in inches. So I'm writing kips per foot. I'm doing that to tell me that X needs to be in feet, okay? This is one of the big mistakes that happened on the first exam was a lot of people didn't write the units. Write them out, okay? I'm serious. This type of stuff matters. All right. So is everybody okay with this equation? All right. Everybody okay with that? Here's another equation that I want to write, okay? Would you agree with this? Would you agree with that? All I did is take this equation and solve for X. So let me explain why these two equations are important. The first equation will tell us what the shear is at a given point along the beam. So that's going to be important to plot the beam, or plot the shear diagram. This one, the one on the bottom, will tell us, okay, if I'm trying to find a given shear value on the shear diagram, it'll tell us where it is. So this will help define where we need stirrups and where we don't need them. And based on a given stirrup spacing, it'll tell us where we can start to use that stirrup spacing. So that's really going to be important for us for design. All right. Sound good? Now, let's also be clear, okay? These equations, I'm going to draw it out. These equations only work for this. Okay? Anytime that changes, all this is different. Okay? So you need to be aware of that. Sound good? All right. Okay. Now, while I'm here, I'm going to compute a couple things. So specifically, I'm going to compute some stuff related to concrete capacity. So how do I compute V sub C? If y'all remember that? It is an empirical equation. Making you all do some research through your notes. Oh no. There we go. There we go. So 2 lambda BW D square root of FC prime. So 2 times 1 times what? There we go. 16 inches. 25 inches. Again, be diligent on that. Times the square root of what? There we go. 4,000. You put in PSI, you get out PSI. What do we got? Now we'll just keep it to the nearest pound. So is that, everybody got a second on that? All right. So that's in pounds. So in kips, well here, we'll just do this down here. In kips, that'd be 50.596 kips. I'm gonna keep the decimal out a little bit. Now that's VC or VC. Phi VC is what? What's phi? There we go. For shear, always 0.75. 50.596 kips. $37.947. Do I got a second on that? And don't clear that out of your calculator just yet because I got one more I want to do. If you recall from the stuff we talked about in relation to shear, we can stop using stirrups once our shear gets below a certain value. And that value is not phi VC, it's half phi VC. So I want to compute half of phi VC right now. So 1/2 phi VC is 1/2 of 37.947 kips, which is sound good? All right. Okay. These values are going to become pretty important here in a second, but does everybody have this? Okay. Now, for the most part, we have everything that we need to just plot a shear diagram, but I want a little more data in order to do this a little more accurately. Does everybody have this? Okay. Okay. So what I want are some important values for plot. Okay. All right. The first thing that I want is VU star. Okay. Now, VU star is just whatever the shear is at x equals d. Okay. So maybe I'll do this. Maybe, hold on. Since this is a function, we'll say x equals d. All right. Now, what was our equation to determine shear as a function of x? We wrote it down a second ago. 115 minus 11.5x. Y'all remember that? So to find the shear at x equals d, I'll say it's 115 kips minus 11.5 kips per foot times d. And what's d? What's wrong? There we go. This is the type of stuff that will mess you up on an exam right here. Okay? So make sure you're aware of that. So what do we got for VU star? I have a second on that? Okay, so when we start spacing out stirrups, we're going to start based on 91.04 kips. We're going to see how that goes about here in a second. Now, that's one value. I also want to know the x at phi VC, and then I'm also going to find the x at half of phi VC. So now how do I find the x at phi VC? Well, what's the equation for x? Okay, so essentially another way of interpreting that is x equals 115 minus whatever shear value we're looking for divided by 11.5. So what I'm going to say is 115 kips minus 37.947 kip divided by 11.5 kip per foot. So what is that? 6.7 what? 6.7 feet, which is how many inches? 80.4 inches. Does everybody understand that? Everybody okay on that? And again, don't shortcut. Write K-I-P, K-I-P, or K over F-T. I mean, write it out. Okay, use your pencil and write it out. All right. So I've got the x at phi VC and the x at half of phi VC. So exact same thing minus, nope, wrong one. What is half of phi VC? There we go. And what do we got? And in inches. Everybody okay with that? Now how long is the beam? 20 feet. So let me just be clear. Our shear diagram, like if I drew a little tiny shear diagram, you know, over here, it's going to look like this, right? This is going to be 115 minus 115, and this dimension is going to be 10 foot, right? Like, we don't need a crazy equation to tell us that, right? Okay. Now, here's where we have some fun. All right. Okay. You know what? I'm just going to be conservative and do this on a new panel. All right. You can go away. Where are the lines? Oh, there we go. Hold on. I'm just getting reoriented to doing these line commands again. That's because I was using the line tool. I'm not that good. Okay, so here's what I'm going to do. Let's see. Is it? So I'm going to draw an axis. Oh, come on. Hold on. I'm going to get there. I'm going to get there. All right, so I'm going to draw this, and I'm going to draw that. Okay, sound good? Now, bear with me on how I actually draw the shear diagram, because I think it'll make sense when I get into it. You go away. Now, let's do the shear diagram. Let's do that in red. And this is how I'm going to draw the shear diagram. I'm going to say it kind of does this whole thing, Oh, well, no. I picked the... Red. There we go. Let's try this again. Oh, my goodness. What the... Oh. Oh, my goodness. This is good. This is going to happen. Okay, we won't use the color. I'll change it later. Okay. I will pick the red line. I don't because it's really... Thank you very much. Well, this is why... This is why I didn't pick the red line. All right. No, I'm going to get this right. All right. This is what I wanted it to look like. Let's see. This should be red. Okay, there, now it worked. Okay, we're not using the pen tool anymore, but I will say that it was probably a good idea that we had the pen tool the first time. All right, so let me just sort of do this. Okay, so now, so the shear diagram should go from 115 to 0. So what I'm saying is that this quantity right here, this is 115 kips. Okay? Now, this quantity right here, this is the 91.04. All right, I'm getting ambitious and we'll try something. All right? And what I'm saying is that this cuts off at a given value. So let me do that, and then now let me reformat. That's how I should have done it this whole time. Okay? Now, I say that this cuts off at a value of about 25 inches. Okay? So, actually, let me see what I can do here. Hold on. What do you mean the axis down here on the bottom? Like this is 0 inches. Okay. This axis is the x, and I'm going to put this in inches. And I'm going to say that this one is the shear in kips. Okay. Is everybody all right with this? Now let me ask you this. What is the x value right here? What's this x value? 120 inches, exactly. So what we'll say is this is 120 inches, and we'll say that this line right here, now that I understand how this works, this is that's the center line of the beam. Everybody all right with that? Okay. Now, we indicated two other points. We indicated phi VC and we indicated half of phi VC, right? Now, what was phi VC? Okay, 37.947. So if I try and go to scale, that's about right there. That about right? I'll give that a different color. Make that purple. Okay. So that's phi VC, right? Okay, now how much was phi VC? About 37.9 kips, right? Now, where did that occur on the line? That occurred about right there, which 80.4. So y'all kind of see where this is going? So this is 80.4 inches. And then this dimension right here, see now you can kind of see why I wanted to use the straight edge. That is about half of phi VC. And that was what, 18.9 or 19.0, something like that? Just for this is close enough. And that was at a dimension of right here. Didn't we? 100.2? Isn't that about right? Okay, sound good? Everybody all right with this? Now, let's talk a little bit. Let's talk a little bit about the three regions. So what I'm saying is we've got three regions of the beam, from here to here. Okay, this region here from 0 to 80.4. Okay, this is the region of the beam where all the shear values are larger than phi VC. Would you agree with me on that? Okay, so anything larger than this is where we have to have stirrups. Like, we need stirrups there to keep the beam safe. Make sense? Okay, anything between here and here, like once we cross this point right here, the concrete takes over. In other words, we technically do not need stirrups past 80.4 inches because everywhere past here, the shear gets lower and lower. Make sense? So that's that region. Now everything past 100.2, we don't need to put stirrups at all. Everybody okay with that? So here is what I'm going to do. I'm going to label these regions as follows. So, all right, so, oh, that's not what I wanted to do. All right, so. All right, so. All that blue. All that blue. And all right. So this region on the very right, what I'm going to say, this is no stirrups required, okay? This region right here, I'm going to say the concrete carries the shear. And this region, I'm going to say stirrups needed. Okay, is everybody with me on that? So what I'm saying is that this is sort of the gut check. If I start laying out stirrups, I can stop, I can go from x equals 0, and I can lay out stirrups until I get to an x value of here, 100.2, and this is where I stop. Okay? Is everybody with me on that? Everybody okay on that? Okay. All right. Apologies for the technical difficulties, but in all honesty, I think it was necessary to get it right because I'm not that good. Okay, does this make sense? Anybody have any questions on this? Okay. CT. CL, center line. Yes, yes. So the beam's 20 foot long. This is till the midpoint. So whatever design we generate over here, just put a mirror and over there. So like the shear diagram for this beam is just well, yeah. I mean, it technically goes down, but in the world of structures, when it comes to design, we don't really care whether or not the shears are positive or negative. We care whether or not the moments are positive or negative because that tells us whether or not we put the rebar on the top or the rebar on the bottom, but this doesn't matter. It depends on the situation. For here, I would just do this because it's symmetric. If it's not symmetric, then we got another thing to talk about. You see what I mean? Everybody else okay with this? All right. What I'm going to do is very quickly propose a design, and then as soon as I do it, I think you all are going to be able to tear it apart and say we could do better. And let's sort of see what happens. All right. Do you agree that we need to provide stirrups up until x equals 100.2? Everybody okay with that? So I'll put stirrups needed until x equals 100.2 inches. Like that right there is going to be our guiding principle throughout the entirety of this example. Everybody okay with that? Okay. If you're okay with that, then let's do a design, and then let's see what's wrong with it. Okay. Has everybody got everything on this slide? We've done 49 slides worth of calcs. All right. So we're going to do step 2 of the design, which is essentially the starting S value. Okay. Now the way I'm going to do that is I'm going to determine the required spacing essentially right here. I'm going to determine the required spacing for this shear of 91.04 kips. So we're solving for what spacing do we need to safely resist that shear. And that is S required is phi AV FYT D over VU star minus phi VC. Okay? Since you're just taking that phi VN has to be greater than or equal to VU, expanding it and just solving for S. That's all I'm doing. Okay? So plug and chug. Okay. All right. VU star was 91.04 kips minus 37 point, we'll just say 95, not 99, 95 kips. All right. Now, if you do this calculation, what do you get? Now, that was pretty good. Pretty good. $4.66. Okay. Now let me ask you this. Do you think you're going to go tell a contractor to space up stirrups at 4.66 inches? No, no, all right, no, hold on. I want to address that. Now, or 4, right? We're going to go down, not up, right? We're going down. If you say S equals 5 inches, a larger spacing is a weaker beam, right? So to keep it simple, just to keep it straightforward, I'm just going to say, you know what, let's just use S equals 4 inches, all right? Now, we'll lay this out, and then we'll call it for the day. Use S equals 4 inches. I would, yeah, keep it simple. Okay, so what we're going to produce, and then we'll call it, is design 1. Okay? Design 1. Now, so we're starting at the very beginning of the beam at x equals 0. Okay? Now, it's very typical to place your first stirrup at about half that spacing. So I'm going to put one stirrup at 2 inches. So one stirrup at 2 inches. I'm going to say it's 2 inches. Okay? So I've got the beam. And I'm going to put my first stirrup right here where this is 2 inches. Then, no. We're going to go the whole way. All right, so we're going to have 4 inches, 4 inches, etc. My question to you is this. How many stirrups do I need to place at 4-inch spacing? No. Up until where? 100.2. And how many spaces do I need? Think about it. 24.5. So why not keep it simple, just say 25? We want to go past that, right? So let's do 25 stirrups at 4 inches, which is, that's 100, right? So in total, that would be 26 stirrups covering a distance of 102 inches. Would that sound reasonable? Now, how many stirrups is that for the whole beam? 52, right? I propose we can do better. We will get better on Friday. What were you going to ask? That's what we're going to do on Friday. We're gonna, like I said, this is design number 1. We're going to see if we can get better. Again, if you cut a couple stirrups out of one beam, no big deal. If you cut a couple stirrups out of one beam and you use that beam 900 times in a building, oh, well, that might matter a little bit more. All right, sound good? All right, so we're going to take this design, we're going to improve upon it on Friday, and then we're going to, once we improve upon it, we're going to start an example where we got concentrated loads and our shear diagram gets a little more tricky. That's all I got for you all. You all have a great one. We will see you on Friday.